Hello everyone, I'm Abasud and welcome to my course on NIST 882 that is corresponding to the Industrial Automation Control, that is ICS security. So let's go forward to understand about this NIST framework. So if we go to next, we want to understand more about what is IEC, that is Industrial Control Systems. So basically these IECs includes SCADA, that is Supervisory Control and Data Acquisition Systems, DCS, that is Distributed Control System, and other control system configured such as PLCs, that is Programmable Logic Controllers, are often found in industrial control sectors. So SCADA systems are generally used to control the dispersed assets using centralized data acquisitions and supervisory controls. DCS generally used for the control production systems within a local area, such as factory using supervisory and control, uh, supervisory and regulatory control. And PLCs are generally used for the discrete control for specific application and generally provide regulatory control. So basically SCADA you can look into as an example if you are having an electric distribution systems. So where you are, meters are distributed in a large area and you want to collect the data on a centralized location, and you can use that is where you can use the SCADA. DLC is where you are having something like a factory. So inside the factory everything is on the local network. So the area from which you want to collect the data is a shorter one. So where there you can use as a uh, DCS, that is distributed control systems. So ICs are typically used in industries such as electric, water, wastewater, oil and natural gas, transportation, chemicals, pharmaceutical, pump and paper, food and beverages, and discrete manufacturing. Discrete manufacturing means automotive, aerospace and durable goods. So this is where mostly we can say ISCs are getting used. Apart, this is a small list. Apart from that, there are various other places where the ISCs can be used. So now let's go forward and then understand what are the security objectives for the ICS implementation. So which is like first one is restricting logical access to IC network and network activities. This talk about, this may include using unidirectional gateway, DMZ, that is dematerialized zone network architecture with the firewall to prevent network traffic from passing directly from corporate and IC network, and having a separate uh, we are preventing it to and having a separate authentication mechanism and credential for users of the corporate and ISC network. The ISC should also use a network topology that has multiple layers, with the most critical communication occurred in the most secure and reliable layer. So it's talking about the restricting local access to ISC network and network security. That can be through, you can say, network segmentation and network segregation. The next is restricting physical access to the ISC network and devices. This is unauthorized physical access to components could cause serious disruption of ISC functionality. A combination of physical access controls should be used, such as locks, card readers and guards. So we should restrict the physical access to the ISC network. So third one is providing individual ISC component from protecting individual ISC component from exploitation. It's talk about, this includes deploying security patches in an expedition a manner as possible after testing them under field condition, disabling all unused ports and services, and assuring that they require they remain disabled, restricting ISC user privileges to only those that are required for each person's role, tracking and monitor the audit trails, and using security controls such as antivirus softwares, and file integrity checking software where technically feasible to prevent, deter, detect, and mitigate malware. So this is what we are having, protecting individual IAC component from exploitation. That can be by using any software like antivirus software or file integrity. That can be enabling the logs and tracking and monitoring the audit logs. That can be through physical access. That can be disabling the default user IDs and passwords. So these all things are there. The fourth one is restricting unauthorized modification of data. So this basically this includes data that is in transit at least across the network boundaries and at rest. So when we are talking about protecting our data from the modification, we are talking about protecting our data, both type of data, that can both states of data, that is at rest at in transit. The next is basically restoring the system after an incident. So it's talk about incidents are inevitably, and incident response plan is essential. A major characteristic of a good security program is how quickly the system can be recovered after an attack. So that's also we need to check if we want to make sure a good system correspondingly we are having. So in between basically we left two, that the one is the detecting security events and incidents. We should be having a security plans and different tools and techniques to detect the security incident. And we can not only detect it, we can basically should have a tool to put the incident over there, and we should have a incident response framework. Next is maintaining functionality during adverse condition. So how we function if there's something wrong happens, that's basically the plan B. If let's suppose there is a if whatever the data is going to the SCADA, and we'll do the commands to the SCADA and sing back to the tool so that they function accordingly. But let's suppose something happens, data cannot be fetched. So in that case, if manually somebody needs to go and perform the activity, so how it can be done. So basically that is maintaining the functionality during the adverse conditions. So this is what we are having as an our our security objectives. Next, if we come to the security design system design considerations, which is corresponding to IEC, that is industrial control system. So first we talk about the control timing requirement. IEC process has a wide range of time related requirement, including very high speed, consistency, regularity, and synchronization. Human may not be able to reliably and consistently meet these requirements. Automated controllers may be necessary. Some systems may require the computation to be performed as close to the sensor and actuator as possible to reduce the communication latency and perform necessary control action on time. The second is geographical distribution. System have varying degree of distribution, ranging from a small system such as local PLC control processor to a large distribution system. That can be a oil pipeline, electric power grids, and greater distributions typically implies a need for wide area. That can be lease line, circuit switches, and packet switching and mobile communication. The third is hierarchy. So we need to consider the hierarchy as well while doing the security consideration. So supervisory control is used to provide a central location that can aggregate the data from multiple locations to support the control decision based on the current state of the system. Often a hierarchical central control is used to provide human operators with a comprehensive view of the entire system. And the fourth one is the control complexity. It talks about often control functions can be performed by simply controllers and preset algorithms. However, more complex system, for example air traffic control, require human operator to ensure that all control actions are appropriate to meet the larger objective of a system. So our fifth is availability. The system availability, that is also called reliability requirements, are also an important factor in design. System with strong availability uptime may require more redundancy and alternative implementation across all communication and controls. Sixth is impact on failure. The failure of a control function could incur substantially different impact across domains. System with greater impact often require the ability to continue operation through redundant controls, or the ability to operate in a degraded state. The design need to address these requirements. Now, our last is safety. The system safety requirements area also an important factor in design. Systems may be able to detect unsafe condition and trigger action to reduce unsafe condition to save one. In most safety critical operation, human oversight and control of a potential dangerous process is an essential part of the security system. So this is what we are having for the today's session. Thank you for joining.